Hello guys, let us today start with the concept of Riemann integral. For that, we require the basic concept of set of measure 0. Let us first define the set of measure 0. By definition, the subset E of R1 is said to be of measure 0 if for each epsilon greater than 0 there exists a finite or countable number of open intervals I1, I2 and so on such that E is a subset of union over n of In and summation over n of lengths of In is less than epsilon. What we mean by this definition? If at all we have open intervals I1, I2 and so on whose measures are means whose lengths are smaller than epsilon and they are such that their union is the superset of E. The union covers the set E and the sum of their lengths is smaller than epsilon, meaning each of these intervals, open intervals I1, I2, etc., they have length very small, so small that it is negligible. One more point I would like to highlight is this is for each epsilon greater than 0. So whatever small epsilon you take, you should be able to generate, you should be able to give either finite or countable collection of open intervals I1, I2, etc. But the sum of their lengths should be smaller than that epsilon. This is the thing, and that is why we call it to be of measure 0. Thus, E is of measure 0 if given epsilon greater than 0, E can be covered by a union of open intervals whose lengths add up to be less than epsilon. So it's very obvious that if you have a singleton set consisting of one point, then surely it will have measure 0. Now let us go for a theorem. If E1, E2 and so on subsets of R1 are of measure 0, then their union and running from 1 to infinity En is also of measure 0. So countable union of sets of measure 0 is again of measure 0. This we mean to say. Have to prove this? So because it depends on the given epsilon, so let us fix our epsilon to be some fixed value. Now it is said that each of these En's have measure 0. So for each n we will have either a finite or countable number of open intervals that will cover En and their lengths add up to be less than epsilon upon 2 raised to n. Now let us take this union over n from 1 to infinity En. Then what will happen? Then covers those union of all those open intervals will cover this union, and the lengths of all those we are saying countably many. So those add up to epsilon by 2 raised to 1 plus epsilon by 2 raised to 2 plus epsilon by 2 raised to 3 and so on, which we know is a geometric progression and its sum will be equal to epsilon. We know the sum of epsilon by 2 plus epsilon by 2 square. By geometric progression we can have it plus and so on. Let me have up to n. So plus epsilon upon 2 raised to n if I say. I have n terms in hand. The leading term is epsilon by 2. So I can say it is epsilon by 2 multiplied by, and the ratio is smaller than 1, so the formula will be 1 minus epsilon by 2 raised to n, epsilon by 2, and this raised to n, and yeah, I'm sorry, this is 1 by 2 raised to n, it's not epsilon by 2 raised to n, so I need to erase it. The common ratio is 1 over 2, not epsilon, and this will be 1 minus half, and as n tends to infinity, this half raised to n will go to 0, so ultimately we are having twice epsilon by 2, which will amount to epsilon. So this is the way we calculate it. And obviously then this union of ENs will have measure 0. Now consequence of the same is, if we have any countable subset of R, then it will have measure 0. Every countable subset of R has measure 0. How will we prove this? So we can consider this to be the countable union of singleton sets. Every singleton set we know is of measure 0. Therefore, countable union of sets of measure 0 has measure 0. So this is what we have. Now, does it always mean that if the set is uncountable, then it will not be of measure 0? Is it so? So it is not so. And I would like to highlight this. There are even uncountable subsets of R1 that have measure 0. For example, Cantor set. Cantor set is uncountable. Still, it has measure 0. Now let us move to the concept of almost every. What we mean by almost every point? So let us deal with this definition. A statement is said to hold at almost every point of closed interval AB if the set of points of closed interval AB at which the statement does not hold is of measure 0. So if I want to say at most every will mean there are few where it does not, and that few is of measure 0. This is what we mean here to say. So let us deal with one example. We are saying f is continuous at almost every point of closed interval AB. What this means? This means that there are few points where f is not continuous, and those few points are really few. So the set, if I constitute of such points, will have measure 0. So let us see again once again the same concept. If E is the set of points of closed interval AB at which f is not continuous, then E is of measure 0 will mean f is continuous almost everywhere in closed interval AB. Okay then, bye for today.